So we are discussing the recent developments on the FUSERO devices. There's 5 different devices. We've discussed them previously. I'm only going to talk about the ones that we've been working on recently. We've been focusing on FUSERO-A, which is the analysis or characterization of subcritical crack growth in window materials. In parallel to this, with what extra time we have, we are also working on pre-construction, early feasibility analysis of tritium generating experiments. So the mission of the FUSERO program, this is a collaboration between the UK and France, UK AEA and CEA, of course, with the Jules Horowitz Reactor. For UK AEA, the mission is to build a radiation infrastructure and the in-house skills to deliver it. We don't have an MTR, so we rely on collaborations and relationships and experience from others and to deliver these experiments. In CEA, well, I guess one of the interests is to expand the customer base to the fusion community. The UK, we have a lot of experience with fusion. We can define and justify our specifications, so it's a very natural relationship. FUSERO-A, what we're looking at is the subcritical crack growth of diffusion-bonded windows. This is intellectual property owned by UK AEA and used in the jet reactor. There's other ways to use these materials, these window materials, but we believe the diffusion bond to various materials, the most commonly purchased material is a fused silica diffusion bonded to titanium, but we've developed a lot of experience with this technique, and we can bond different window materials to different metallic frames. Something worth highlighting is that in this program, what we're going to be delivering is experimental evidence of the performance of these windows in, of course, neutron and gamma flux. With the existing work, which irradiates these materials under a gamma flux, there's a publication right there, and comparing that against non-irradiated experiments, Sarah is going to be presenting on some of our recent progress on that next, but also some of the previous work that some of our previous secondments have done. We can fully characterize the performance of these important components. You find these components on a port plug of a fusion reactor. In ITER's case, the component looks something like this. The window material can be both either fused silica or diamond. Fused silica, diamond, you can tune its mechanical performance to be essentially indestructible compared to the materials that you find around the window. But for fused silica, which is more delicate, it's softer and you can polish it. So you can actually have better optical performance with fused silica windows, but exactly what material combination or window material you want is a detailed question that requires thoughtful specification and justification. We're of course doing this in the Jules Horowitz Reactor. And in this study, we're going to go through the first iteration of our design process. We are selecting these 2 positions here, P612 and P623, for our analysis. This is essentially a hot and a cold location. Lionel discussed, he mentioned how intense the gamma flux is in the Jules Horowitz Reactor, and in this presentation we'll see the consequences of that. These positions are useful for us. This is of course the core, where you have a rich neutron environment where the beryllium reflector reflects the neutrons back to the core, where you have a high neutron density compared to any material test reactor. But that leaves many of the gammas for the reflector region, and so you have a low neutron to gamma ratio in these locations. This right here is the zircaloy screen, which is supposed to block some of the gammas, but it still lets a fair number through. So these locations, they're good for us because what we're looking for, what we're seeking to do is characterize the subcritical crack growth of windows, which is essentially creep for brittle materials. So we don't need very high flux, but we need to characterize the fundamental performance of this material. So we have to manage the high temperatures in this experiment. We start with our design of these experiments by defining the interfaces between our device and any other component owned and operated by CEA. So here, these are engineering parameters that pertain to how we remove heat. There's a bit of a nice little detail of where we might do all of our manipulation from, sealing, whatever. Other little details that are useful, but all the devices obviously are different, but they're conceptually the same, where you have a tube with experiments located in the active region. The active region is 600 millimeters tall, and it's within this region that we put our experiments. Zooming on to these black boxes here, you have, in our case, some capsules that look like this after only our first iteration. This is we're not committed to this, but this is it represents conceptually the geometry that works for us enough, but is also a valid input for 3D neutronic calculation by the very skilled CEA neutronic engineers. So we passed something like this to the neutronic engineering team, and they run neutronic calculations in the Topaz supercomputer in France, a very powerful computer. And out of this computation, they send us heat loads that we use in our iterations. Something I want to discuss, I want to point out to those in this room, is that what we're showing here is how much the gamma heat deposition changes from one edge of the reflector device to the other edge of the reflector device. So that's from this whole span here is 10 centimeters. And if you look at the average heat load, the mean heat load right in the center of the tube, the side closer to the core is receiving 26% more heat than the side further from the core. So the side further from the core is receiving about 1/2 the heat of a point only 10 centimeters away from it. So that's the distribution from within only one 10 centimeter span in the beryllium reflector. So we take those heat loads from the neutronic calculations, and in our first iteration we pass it into a very simple 2D steady state heat conduction model that gives us a temperature distribution. For this first iteration, I'm going to highlight that what we did, in this model we didn't actually include the changing heat deposition from gamma profile in the model, as that would require a third dimension to enable to allow azimuthal heat conduction. So what we did to keep our first iteration very simple and quick and efficient is just running the model at 1.26 and 0.74 gamma heat load, and we're just saying it's uniform across the whole thing, and that gives us an upper bound and a lower bound for our first iteration. So what we're showing here are results from the hot and the cold positions from both the 1.26 and the 0.74 gamma heating circumstances. So this is the hot position, this is the cold position. We're going to look at the hot position first and kind of look at the consequences of some of our choices here. So in capsule 1, what we have is a shell of Inconel, which is 60% nickel, and this material has very high gamma heating for specific reasons. The shell is only 3 millimeters thick. The only difference between C1, C2, and C3 in terms of engineering decisions are the Inconel shell. The other thing that's different is their location. C1 and C3 have close to symmetric energy deposition profiles, However, due to the decision of Inconel versus titanium, you have a hotspot here, which is 1030 Celsius compared to a hotspot in the bottom capsule at about 600 Celsius. So that's a good evidence of how important very small and detailed decisions are when you're designing capsules. So this is the hot position and cold position. I should mention that our specification, target specification for temperature is between 100 and 200, so this will not work. So we have no choice but to go for the colder position. Still too hot, but you can see with our Inconel decision, our peak temperature, based on how I described, we set up our model earlier, is somewhere between this temperature and this temperature. Still too hot, but with our titanium capsule, it's a little bit better. So this is a good first iteration. It's enough for us to think about what we're doing next intelligently. So this highlights a bit of kind of the outcome from the first iteration. Key takeaway is our temperatures range from 170 Celsius to 1030. What's good is that we possess the what we need in order to make decisions, in order to make this experiment work. I'm going to discuss very briefly this calculation. So this is what we have going kind of in parallel to our first project, kind of in when we have downtime between people running calculations. We're kind of setting up calculations to enable conversations about the feasibility of tritium generating experiments in the Jules Horowitz reactor. And I'm only mentioning this here to enable conversation in one of the workshops tomorrow, as feedback from our colleagues on this is what we need to move it forward. So conclusions, I want to say is that we need to develop a second model, a 3D model that includes the changing gamma profile, and I want to confirm that we have in fact done that, and that model looks really great. And from this, we can make some decisions. It seems that we're going towards needing to put in some kind of shielding, maybe tungsten heavy alloy, in order to get to the temperatures that we need. But yeah, we're making rapid and efficient progress with the time that we have. And that's due to the efficient relationship that we have with the CEA team. It's a great pleasure to work with the engineers there. And some acknowledgements. I want to acknowledge that this program is 11 or 12 years old, started by Gilles Bignon and Christian Collin, Chris Hardy. Christian is here today. Gilles, as you know, retired, but it's great to contribute to this program that is a collaborative effort and is made up by small contributions from many different people. So, on to the next. Oh, and we were invited to a podcast where the FUSERO program, the discussion of the relationship between France and the UK on our collaborative efforts for this was the topic. So please scan this QR code and take a listen to our podcast. Thank you.